Hello all. So today I'm here. I'm going to be going through problems out of this book that I bought from Thrift Books. It's by Walter Jung, and it's all about op amps and such. I think it will be really good. The beer that I'm drinking is Golden Crush from Rebellion Brewing, I believe. I had to get it. I brought it here because the liquor store, it's in this one. I know it says Paddock Wood there. It's not Paddock Wood's beer though, I'm sure. But in the liquor store, they didn't have the cap for these big ones. So they went and they put saran wrap on it, which wasn't all that sure if that was legal. But they suggested it, not me, and I was perfectly fine with it. Anyways, I'll pour it out here into my cup. You won't be able to see it very well though. There. Here. You see, you can sort of see a bit. It's getting the nice head there. No. Very nice. So today, like I said, we're just gonna do some circuits. I've read through most of chapter 1 here, or at least part of chapter 1. Of course, is the most basic chapter. But there's just so many different schematics in here. And as you know, I like trying to explain things off the cuff in a fairly relaxed manner. So that's what we're going to do. And we're, of course, going to set it up in the Falstad simulator and just see if my expectations are correct. So we will start like on here on page 1. I don't know if you can see that all that well. Probably not. You can see the lists are the voltage gain is infinite. The input resistance is infinite. The output resistance is 0. Bandwidth is infinite. And there is zero input offset voltage. So I'll explain that here in a second. So if I draw active components, active build and draw blocks. So this one here. So this is the op amp that we're going to be dealing with. The first page of the book basically goes over saying that the gain is infinite. So that means that the difference in these 2 points can be amplified to infinity on this part of the circuit on the output. The input resistance is infinite. That effectively means is when we are analyzing the circuit that no current flows in to the inputs. So 0 current in the inputs, and output resistance is 0. So that just means that there's no, we shouldn't consider any resistance here on the output. It shouldn't be generating any heat or something to make that output. And bandwidth is infinite. I would assume that means that we would have the as much current as we want coming from it. And then here's the one that is also really important for circuit analysis, is there's 0 input offset voltage. So that means there is no difference between these 2 voltages. So if I tie this one to ground, which I will soon, it will be, this one will also be at ground. It's called a virtual ground. I'll have a nice drink of my Golden Crush now. Okay. So, the first circuit on page 16. Oh, no, that's not the first circuit. First circuit is actually on page 17. By the way, that first page was actually page 15, but it's the first page with real content in. So, we have to draw. This is what is called the inverting amplifier. So if I put this here, cuts here. But anyways, we now go put an input in. Might as well put a 1 voltage input. Oh, wait, stop. Yeah, so there, now I'm at this 1 voltage input. So let's think. I'm gonna use one of my cucumber garden markers. I actually improved on this design now, but I'm gonna use it for now. I'm gonna use it as a bookmark. So let's just think of what I just said before I simulate it, which well, I already did start simulating it, so that is unfortunate. But here, let's just reset it. Now we can think just ourselves here. So if this is 5 volts here, and then this is at ground here, well, one of our golden rules of op amps, as said in this book and almost every other book, is that this voltage and this voltage are the same in a perfect op amp. So we'll assume perfect op amp here, an ideal op amp, because usually that is appropriate. So this is 0 volts here. And we also know no current flows in to this input. So that means this 5 volts has to be down to 0 volts by the time it gets here. But the current will still flow. So effectively, we're going to have 5 milliamps, because 5 milliamps times 1K is 5 volts. So that means there's minus 5 volts here, gets us to 0 volts. But then this 5 milliamps will keep flowing. So that means that there has to be, because this is another minus 5 volts, that means that this has to be minus 5 volts being outputted. So let's just run that. And yeah, as you can see, the current flows this way, minus 5 milliamps, and the voltage is minus 5 volts. Let's just stop this. Let's say we change this to 500 ohms. Okay. Now what do you think will happen? Well, let's say, again, using our golden rules, this is still 5 milliamps traveling through here, and it still has to keep going. This is only 500 ohms now. So that means that this is going to be minus 2.5 volts, because 5 milliamps times 0.5K, which effectively 500 ohms is 2.5 volts. So there's 2.5 volts that's burnt across here. That's minus 2.5. Then we get here to be minus 2.5. Let's see if that's right. Yep, minus 2.5 volts. So there's that one. I'm just gonna have a drink of my beer here before we move on to the next one. If anybody has any questions, this is a good time to ask them. I'll see if I can answer. No? No questions? I'll just have another drink there. I do love my beer. So then we shall move on to the non-inverting amplifier. So I'll just stop this. Now delete this. Oh, oops. That's wrong. Move this up here. And then add Inputs and sources. Add voltage source. And add it right there. So now, yeah, I'm just going to change this to 1K. Edit 1. Okay. And I'm doing that just because I know that 1K is always nice and good math. So, now we have a different situation. This is at 5 volts, right? That means that this will be outputting. Here, I can. No, that doesn't matter. This will be outputting whatever it can to get this up to 5 volts. So that means that this will have 5 milliamps coming out of it at 5 volts. No, we'll have 10 milliamps and 10 volts there. Ah, frick. Okay, I am gonna delete this just because it's confusing me. Sorry. So now, yes. Let's look at this again. This needs to be 5 volts here. And this is in total 0 volts. So that means, like this going through here has to be 0 volts. So whatever this outputs has to be 0. So in the middle, yes, this will have to output 10 volts. Let's just try that. And yeah, 10 volts. Now that shouldn't actually change the answer that when I got confused there. Remember? If you were paying attention. Add resistor. We'll just add all this in. Outputs and labels, inputs and sources, this one. So you see, it doesn't change our answer for the voltage question. Because this voltage will stay at 10 volts. There will just be 10 milliamps traveling here. Up here, it will just be 5 milliamps. That goes to, I believe, what they called the bandwidth. Infinite bandwidth of it. This is a very nice beer. Golden Crush of Rebellion. Okay. Now, what do you think if I change this to 500 ohms? What I can do is just go here. Edit 500. Okay. Let's think. If I change that to 500 ohms, that's 0.5K. So in total, it would, so instead of taking up half of it, it would only take up a third. I'm expecting, 7.5 volts. Because then, so that 7.5 volts, that'd be 1500. So effectively, but okay, the real reason I picked it is because that means that 2.5 volts gets burnt across here, 5 volts get burnt across here. And since this is 2 times the size of that, I think that should work. Okay. Yeah, so 7.5 volts. How many milliamps is it? 5 milli, right? Yeah, you see that is where I need to get it through. That's a really good way of looking at it, actually. Is that to get 5 volts here, down to there, you're going to have 5 milliamps. So whatever we choose this to be, so let's say we choose it to be 2K. So now, if effectively, we are going to have 5 milliamps traveling across 3K. So that means that we have to have it be 15 volts. Let's double check it. And yeah, 15 volts. That's actually a very good way of thinking of it. So is there any questions, comments, concerns? Nothing? Okay. Let me go check on the next. Oh wait, I'm not there. So now, it's going to talk about the differential amplifier here. This will actually take some putting together. So, just bear with me for a bit here. I'm going to delete that. I'll stop this. Please feel free to comment. Either just profess your love of op amps, or ask questions about them, or whatever. Ask questions about the Roman Empire too, if you want. I do like the Roman Empire. No, that's a bit off topic, but I just want to put it out there that I would not be insulted if somebody came to this live stream about electronics and started babbling on about Rome and how Marcus Aurelius really should have done better. What's the term for it? Estate planning, basically. But I was not there, so I didn't get to tell him that he was being an idiot. So we got those two. Then it just applies two different voltages. This one goes and gets applied to the ground. Some sources, ground. At ground. Okay. And apologies that it takes so long to set some of these up. I'm thinking of doing a similar type video as this, but not live. I'm thinking of doing like this, but instead doing it with actual real components. I think I've mentioned this before. I've considered doing it live before, but then I sort of decided against that because I think it would be like way too complicated. Yeah, maybe let me know what you think about that. I think it'd be fun. So, let's look at this circuit. I think I got it all set up correctly. Double check. Well, I got them all the same. This is a much more complicated circuit. It might be hard or next to impossible for me to explain it. We'll see if I can. So basically, what we'll be setting, the voltage will be this side, the equation. They call this the differentiator, by the way. Because this is obviously defined on how much current's going to be flowing through and what voltage will, I guess, be set here. based on that current in this resistor. So because we have two 1K resistors here and 5 volts there, that means 2.5 milliamps will be flowing through here, and that means 2.5 volts will be checked here. That means 2.5 volts has to be here, which means that it's just going to be 5 volts out of here. No. It's going to be 0 volts. It's going to be 0 volts right here, I bet. Let's run it. Yes, 0 volts. So we'll stop. That isn't very exciting. Not exciting at all, really. Let's make this exciting. We'll make this 500. Okay. So now I paused it just so that now we have to think about it before we try it out. Now, this is... well, that's not very good. Let's edit this. So that's 1500 ohms. Let's make this 15 volts. Apply. Okay. Then I can say that there's a milliamp coming across here. So effectively, there's going to be 5 volts right here. 5 volts there. Yeah. So that means, since there's 5 volts here, there has to be 5 volts here. That means there's going to be no current. I wonder if there's just going to be nothing. Yeah, there's just nothing. Well, that's not very exciting either. Stop. Let's jack this up to 2K then. Apply. Okay. Move this down to, I don't know, 500. Okay. And change this to back to 5. We'll go back to 5. Okay. So that's 2.5K. And we have 5 volts. So that means we're going to have 2 milliamps coming across here. 2 milliamps times 500. That means a volt will be spent across this. That means 4 volts will be seen here. That means that this will have to have 1 volt. Or what? 1 volt will be burst off across it. So that means that we're going to have a current of 1 milliamp here. And means that will be 0. No, 3 volts. Right, 1 milliamp. Yeah, sorry, I was being stupid there. 1 milliamp is going to be traveling here. So that means 1 volt will be spent across here, which will be 3 volts. Now, let's stop this and move it around. Okay. Now we're basically flipping the script here a bit. We are going to have only a single volt here now. So 1 volt. That means 4 volts will have to be spent across here. That means 4 milliamps. That means 4 volts will be coming across here. So, I mean, since there's only a volt here, we need 4 volts to be spent across here. That effectively means we're going to need a minus 3 volt here. See? Yeah, minus 3 volts. So, I think I might move on again. Unless anybody had any questions or comments. Concerns? No? Okay, let's go on then. This, by the way, is the Falstad simulator. If anybody's looking to use it, it's a very, very useful simulator, and it's free online for anybody to use. I love it. I use it all the time. So now we are gonna do the summon inverter. I will stop this, reset. Keep that the same. And basically, oops, no. So now, this is just a little bit different. We're going to move it down here, because what I'm going to do is now add a bunch of resistors. Oh yeah, I don't have to reselect it. And voltage sources. Now, we'll keep them all the same for now, but we probably are going to change them later just for demonstration purposes. But basically, now we are going to have, because this has to be at 0 volts. So that means each of these points will have to be at 0 volts. That means 5 milliamps is coming from each of these, which means this is going to have a total of 15 milliamps, which means that this will have to be up to 15 volts. Let's see. Yep, minus 15 volts. Now the problem that we'll get to, you see, I'll just demonstrate this because I know what's going to happen. Because I've used the Falstad simulator before. I'm going to apply. Okay. So now you see this is getting all that there. And basically this isn't being able to keep up, because it's only set, its power supplies are only set to plus or minus 15 volts. Now you don't see that here because it's normally implied, but you can actually edit it, and I can go minus 100 plus 150 or whatever. So now you see we're at 50 volts, so it's good, but that's just silliness. Let's move it back, and then I'll go here. 2K. So now we have the same situation. Now it's an inverted. You can see where the name comes from, the summon amplifier, because it is basically taking the sum of each of these currents and creating a inverted sum. So like whatever that sum is, whatever it needs to make that voltage, it inverts it because it's the inverted input. So in this one, we'd have 4 milliamps coming. This one, we'd have 2.5. So that means we'd have 6.5. And then 5 milliamps. So that means we'd have 11.5. So it should be minus 11.5 volts. And yeah, it is. Yeah, so that's a really cool circuit to demonstrate things. Does anybody have any questions or comments on it? Again, this is the Falstad simulator. If anybody's looking to simulate circuits, and it does a whole bunch of different things. I might show some example circuits that it just sort of has in stock. Once I get through, we're almost at the point where I've stopped reading the book, and I don't think there's too much ahead until later, and then we'll go in and we'll talk more about it after. For now, nobody has any questions, might as well move on to the integrator. So basically, I will stop all this and then reset it, delete that. And now, instead of this, we are going to draw in a capacitor. Now, what do you think that is going to do to our circuit? Just think of it for a second. And here, I think it's better. Yeah, where they put in. So it's probably better if I, instead of doing that, go draw outputs, labels, input sources, AC voltage source. So I'm gonna do that. Please add wire. Add wire. Now I can edit this waveform. I'm gonna make it a square wave. Max voltage. Okay, apply. Okay. So now that I have that set up correctly, we're gonna be doing a square wave of 5 volts. Now, what do you think happens when it's going up 5 volts? Well, here, I'm gonna actually add a scope here. Outputs and labels. Ooh. Ah, sorry. I don't want that. Draw. Where's my test point? I just added the test point. There, test point. Right there. Then I can view a new scope. So there's our scope. So I'll see if I can actually explain this well. I'm getting better every time I do it. I can come up with a better explanation. I think so. Basically, what does a capacitor do? It changes, or it resists changes in voltage. So it's gonna slow it, and then this will want, here, let's just run it. So yeah, that's what we're going to be getting. So you see here, I can see goes from 200 microvolts. Yeah, so it keeps on changing because this is changing. This is always at 0. But this voltage here is changing. Okay. So oh wait, yeah. So I shouldn't think of it that way. Okay, that's a better way to explain it, I think. Is okay, so I was thinking of a sawtooth, but we're generating basically a sawtooth right now. Let's just stop it for a second while I try to explain myself. So if this is at 5 volts, then this is going to be transmitting 5 milliamps. That means that this is going to shoot up to whatever its max is to try and get this back to where it should be. So if this is at 5 minus 5 volts in that case, then this is going to try and sees minus 5 volts. That means it's going to output 5 volts to try and get positive voltage there, right? Let's see. So this is, now it's at 5 volts. It's at minus 5 volts. So here, now we're at the 5 volts. I'm sorry, I'm stumbling over this now. I think if we slow it down here, to like, you know, actually we could probably, here, cancel. We can go here. What's simulation speed? There, yeah. So we can slow down the simulation speed to get a better look at everything. So we're at minus 5 volts. This is driving it up in voltage. And then it's 5 volts. So you see, I think, so this should be an ideal op amp. Because now it's trying to drive itself down. Shouldn't it go down to minus voltage here soon too? Actually, no. No, that is right, I think. This will be at 0 volts, so then that's going to be... Yeah, I'm generally trying to think of it with its, with the, whatchamacallit, the golden rules. So, if this, and you see it's just barely getting there, but there's no... I'm gonna have to think of this more. I've thought of it lots, actually. But, you know, let's go in and do, look at the ones from Falstad itself. Because I'm at, yeah, so now in the book it goes and it starts talking about non-ideal op amps. So, I think we can just go on and do some other ones for the rest of this. Let's see, we got circuits, op amps. Let's find there's the integrator. So this is what it puts up for the integrator, which is an even more complicated circuit. But it does follow the same ideas. It would follow the same ideas. I don't know why they have two things here, but these two tests an integrator. So that means that it is, like, when you got this, you'll get, like, the integration of 5. No, maybe not. But, so, that is a good way of thinking of it, too. This is one of the downsides of looking at it while you're having a beer, is sometimes your mind doesn't work as well when thinking about it. It does, I say that, but it does work in other ways nicely, in that I think I generally rely more on intuition, which in itself is very good, I find. But let's go to a different circuit here. Peak detector, that's a nice one. It's a gyrator. I'm not figuring out what they're trying to do here. Doesn't make sense to me. Let's go to a different one. Actually, no, let's Google gyrator. Circuit. Okay. So a gyrator is a passive linear lossless two-port electrical network element proposed in 1948 by Bernard D.H. Telgen, the hypothetical fifth linear element after the resistor, capacitor, inductor, and ideal transformer. It inverts current and voltage characteristic of an electric component or network. Odd. Okay. I hadn't ever heard of it actually. Let's go back to op amps. And here, I'll do a peak detector one just because they are cool. So a peak detector, it basically detects a peak, and so like if I go here, so now it's detected a peak. What this is doing would be, yeah, it's the highest voltage that was at the time. 5.7. Go there. And that this resets its voltage peak. Basically would take the lowest. We go inputs and sources and noise generator. Let's do a noise generator right here. Oh. Doesn't like that because I broke the circuit. Okay. Let's go Control Z. Run, stop. Sorry, I broke the circuit. I used noise generator. And it basically said, oh, there's no resistance here, so it was insane. How can I? Let's just update this to a max of 5 volts. Apply. Okay. So now you see we're gonna be able. We have got the 8 there. So this circuit, basically, whatever is the highest that it finds here, it will hold it. And it's because this capacitor, because this will of course not accept any current. This capacitor will quickly charge to whatever this starts outputting. And then as soon as it's charged to that, if this starts outputting anything less, this diode blocks it. Let's just go and keep upping it here. Go 50. See, it's but I can't do it again because this doesn't have. Questions or comments? This again was the Falstad simulator, and I hope that you had fun.